Our next speaker you might know from her every other week iOS code review. If you don't subscribe, you should. She's been advising startups lately. She's been developing forever. And she also is a mentor, so she's mentoring teams. When she's done taking her selfie, I will introduce you to Marina, who's going to talk to you about bug-free by design. Marina.
Awesome. Thank you. Thank you. All right. No. X. Yeah, there we go. Cool. So, hi everyone. My name is Marina, and welcome to my talk about crafting bug-free Swift code. So, let me first introduce myself. Daniel did a little bit of that, but I'll just throw a bit more information. So yeah, my name is Marina. I go by Hybrid Cat online. That's after Hybrid Theory, an album of Linkin Park, which I used to love when I was 15 years old. So then that stuck with me. Yeah, so I've been building apps for iOS since 2011. My first project was using manual memory management, so I've seen things. And since then, I worked in a couple of startups and companies like Citrix, Storytel, and Novo Nordisk. And these days, I'm independent. I'm mentoring teams and advising startups, so I try not to join companies full-time. I try. And also in my free time, I'm curating a newsletter called iOS Code Review, where I'm sharing code improvement tips with the community every 2 weeks. And these days, there's around like almost 3,000 subscribers. So I'm trying to grow that project as well. And so during my career, I worked on a couple of dozen of different apps. And I have developed a style of writing Swift code that's bug-free by design, I like to call it. So it eliminates certain types of bugs, basically preventing them from compiling. And today I want to share a few of those techniques with you. And I hope you can use some of them in your projects already right after this talk. And if not, I hope you at least get inspired by this mindset. So first of all, let's talk about what is good code. What do we mean by that? So usually we mean that good code is readable, meaning that it's easy to understand and it's easy to navigate around. Then good code should be maintainable, meaning that it's easy to change. It should be testable, meaning that it's easy to verify using automated tools such as unit tests and integration tests. And it's nice to look at, which is subjective for different people and different teams. And sometimes that's around where this discussion ends. But I feel it's really important to talk about that good code is also correct, meaning that it does what it is intended to do. It's also robust, meaning that when we change it, either because we're refactoring or because we're adding new features, that code doesn't break and still keeps doing what it was intended to do in the first place. And then good code should be performant and serve better UX. For example, have accessibility built in, and that's what we get with Swift UI. And today in my talk, I want to focus on these two things, the correct code and robust code, and show you a few techniques there. So how do we usually check that our code is correct? We test it. We test it manually or using automated tools. But wouldn't it be nice if the code that has bugs just didn't compile? And that's what I want to focus on today. And of course, that's easier said than done. We often say, the only perfect code is the code that doesn't exist. But unfortunately, that's not exactly where we can be with our jobs. We still have to write code, but we can try to make as much as possible, as much code as possible that doesn't have bugs, and then add testing on top of that. So, Swift comes to the rescue. We gladly have this not so new anymore, but Apple has gifted us with this language instead of Objective-C that allows us to write much safer code. And it has all these features such as strong typing, optionals, immutability, enums, better control statements like defer and guard, and access control. And what I want to show you is how we can combine these things together to fight certain common issues, common bugs. And I will show you concrete examples of bugs we face and code examples of how we can write code to solve them. But first, before we do that, I want to take just 2 minutes to quickly run through these features as a refresher, just so we kind of remember after lunch what these are and don't fall asleep, hopefully. So we have strong typing, which checks a lot of things for us. The compiler checks that things match, which is not the case in a lot of languages. Then we have optionals, which force us to declare missing, that a value can be missing for this variable, and they also force us to provide either a default value or explicitly handle what happens if there's a value and there's no value. I'm not mentioning force and wrapping, just pretending that doesn't exist. Then we have a guard, which solves a previously common problem of falling through to the happy path when we're checking our preconditions in the beginning. Now Swift checks that we have written return or thrown an error explicitly. Then we have immutability, which first of all allows us to make sure that the constant is only set once, or so set either right away or once before it's used first. So we don't have to provide the value until it's used. Then we have access control that, just checks that we can't access things outside of the scope of that type where they're defined. So we have a bit better code boundaries. And we have all loved enums, which previously, and in many other languages nowadays, you'd have to use various variables to represent the different amounts of state, which ends up in being an exponential amount of combinations, which cannot really happen in the app, but we kind of still have to handle them in our code. Today we can just list exactly the types, the states we have, and switch over them, and the compiler can check that we are switching over all of the cases. And then we have the defer, and this is the last one here, which allows us to set up the cleanup block that is executed at the end of the scope where we define that, so a function or even an if statement which has its own scope, so we can use it there. So that was a quick run through. Let's now see how we can combine these things together to fight common bugs. I loved that cartoon when I was a kid. So let's start with defer. So how many of you, please raise hands, have used defer in their production apps, code bases? Cool, so it's about a third. Nice. So I hear a lot from my colleagues and people in the community that they know what defer does, but haven't really used it. So today I want to show you a couple of examples how we can find common issues using defer. So first of all, I have an example here with rendering an image, like custom graphics into a UI image. And what we have to do is begin image context and then end image context. And if our code for the rendering pipeline is complex and has many exit points, we need to make sure to call end image context at each of those, because otherwise we'll have a memory leak. So using defer here is a perfect solution for making sure we do that in every branch of our logic. And we could say that it's easy to just write, the end image context in every place, but when we change the code, so now coming back to the code being robust, when we change the code, we can be completely free to change the rendering code below and just being sure and safe that our code can be relied on. Then another example is kind of similar with writing to files. We can open a file or a stream and close that in the defer right away, and then we can focus on our happy path logic. And this works with async await too. So the scope exits when the function ends, including all of the async operations in between. So if we set up the defer at the top, then it will do all the async things and only execute the defer at the very end. And now, one more example, last example of the defer is writing heavy files to disk. So when we write a file that's, many megabytes, possibly gigabytes, that can take a few seconds. And the user can put the app to sleep, like minimize the app while that write is happening in the background, like in the background thread, because probably, hopefully, you're not blocking main thread with a multiple second write of a file. So, and if that happens, if the user puts the app to sleep, then we might end up with a half-broken, like half-written file, which would be broken and cannot be read by the app later on. So what Apple advises to do is to wrap such operations in begin background task and end background task. And what that does is, if the user goes to sleep, puts the app to sleep, not goes to sleep, which could be related, but not necessarily, then the app will see if there's any outstanding background tasks at that moment. And if there are, then it will allow us up to 30 seconds extra background execution. But if we don't end the task within those 30 seconds, then the app will be killed in the background, and when the user relaunches it, it launches from scratch. And that's an issue that is like, I don't even know how you would track that. How would you catch that, aside from looking at the logs? So setting up something like this with a defer, so we create, let's see if I can do pointer, yeah. We create a background task and immediately set up a defer to close it, and then we can focus on our writing. And even if it succeeds, even if it fails with a throw, the defer will be executed in both of those cases. And there's, the QR code there is a link to documentation of begin background task. It has everything I just said is described there quite in detail, how we should, that we should wrap all of these heavy operations into begin background task and background task. So it's a really cool, cool technique that I think all apps should use, actually. All right, so that's defer. Let's move on to looking at UI updates. So unlike defer, I bet this type of code all of you have written. At least I have written that many times over in every single project that uses UIKit. So we define a state with all the states of your UI component and the corresponding subviews. And then at one point we are iterating or switching over the state in the update function and configuring the different subviews according to the state. And you probably can't notice, but there's 2 bugs in this code. And here is the fixed version. Can you tell the difference? I'm not going to ask. I think it's extremely hard to read, and if we're doing code review on this code, or if we're working on changing this code, it's my brain always breaks. So yeah, let me just highlight the issues for you. The isEmpty check is flipped here, and we're missing an error label configuration there in the else clause. And those true and false things at the top, they're probably correct, but I decided not to check them. To make a point, let's refactor this code to make Swift compiler catch those bugs for us. So I have the same function, and what I'll do first is define the 3 let variables. I'm not giving them the values right away, and they will represent the configuration for each of the subview. So for example, data text, I made it an optional string, so if the value is there, the view will be visible, and if the value is not there, then the view will be hidden. So then I'll switch through my states and assign these values. Click, click, click. It's going to take a moment. Yes, it's a very loud click. Right, and then after the switch, we will give this configuration to the corresponding views. So, you know, the error label gets the text and the visibility, the spinner gets the visibility, and so on. And this is a simple example. You could do more things here, like for example, if there's a shadow in one of the cases, like on one of the projects I'm working at just a month ago, a designer wanted to have a shadow in one of the states but not in another. So then you could have an if should show shadow, do one thing, else have all your shadow configuration code after the switch. And this was readable, but let's see how that can highlight errors. So I have the same function here, just shortened a bit. And here's a bug. Like show spinner bool is not set to any value in one of the branches. And what the compiler will do is it will show an error saying like show spinner is not set before it's being initialized. because it checks that it should be set only at this point. It doesn't care before that. And so the compiler basically caught a bug for us. Then, because it's a let, if we try to set one of those values second time, the compiler will tell us, you cannot set it the second time. And that's an issue that happened to me a number of times when you're refactoring a complex code, because here's just 3 different examples. It could be 4 or 5, or different subviews. Sorry. Yeah, so this is enums and late let to help us make more consistent UI updates. Now let's take it up a notch and have a look at completion handlers. So this is a type of code that, again, all of us have seen, I would bet. So the data task, and then and the completion of that, we will look at the different errors and the status code and so on. And this is actually a common interview question as well, where they show you this piece of code and they ask you, do you see any issues here? And this code has a number of them. So first of all, we're not switching to main in some cases. So in the missing data case, we are switching to main, to the main queue, and in the cases of other errors, we're not. And then we're completely missing completion here. And this is a very common issue. I bet a lot of you have seen. I have encountered that a lot. So while for interviews it's kind of fun, like in our day-to-day work, we don't really want to be solving riddles like this. We just want to focus on writing code that we can rely on. So let me show you how I like to refactor this code. So I'll have the same function and the same data task, and then I'll define the result, not giving it the value yet. And then I'll set up the defer, calling the completion handler exactly the way I want, with the main, switching to the main queue, and then calling the completion handler. And you might ask, like, we're not setting the value of the result yet. How is the compiler not complaining that the result is used? And gladly, Swift compiler is smart, and it knows that defer will be called at the end of the scope, so it's not complaining at this point. It will check all the code in the function below. So now that we've set up our result and defer, then we can write the same code or similar code to before, going through all of our checks and assigning the results in each of the branches. So now let's see how this code can catch a bug for us. So if I, just for an example, comment out setting of the result in the data case, the missing data case, then immediately an error comes up at the defer level saying that the constant result is not set in one of the cases. So we have to check our code below. And I really hope that, I guess I should maybe try to contribute. I wanted to say that I really hope that the Swift compiler gets improved and can actually show us which of the branches is missing the assignment. Yeah, that could be a cool contribution, I guess. Yeah, so this is defer and late let, helping us always call the completion handlers. So we have just a couple of more areas left. They're going to be smaller than the one we looked at so far. So next, I want to talk about safer identifiers, and this is the third section. So we work with identifiers in our apps a lot. All our RESTful APIs, they go off identifiers. Like we call the API get user by ID, book ID, order ID, everything is ID based. Then we pass these IDs around in our code a lot to functions, to load things, and so on. We store them in our memory as properties on our components, such as which entity ID this view component is about. And then we have them in codable models and possibly also in like core data and so on. So IDs are everywhere. And the kind of default way of going about it is to define our IDs as their corresponding type, so string or int in some cases. But the issue with that approach is kind of everything is a string, so we can pass any ID to another function that takes kind of ID of another entity, and then discoverability is kind of lacking there because it's hard to search for things. Like in this find user ID string, how do you search for that through your through your project? Do you search for string? Then there's like a ton of strings in the code. So the next step we can do is define the type alias. That helps with discoverability. We can now search by user ID with a capital U and find the uses of that in the code. But here the problem with passing things is still kind of a problem because it's all still strings, so we can pass an ID of order to the function that takes user ID. So what I like to do is define strongly typed IDs. So each ID is its own type. User ID, order ID, they're not compatible, so we cannot by accident use one instead of the other. The compiler tells us you cannot match them, they don't match. And it might seem like a lot of work to set up, but I have actually found a way to, I'm not claiming that I have invented it, but I have kind of got used to a way of doing it that is quite simple to set up. So let me show you how it is. So I would define simple ID protocol that has a backing value. I would just call it raw value just because Swift already has raw representable that's similar. And then I'll have one small convenience function just so I don't have to type out raw value out there every time. And then I could just start defining these structs. On an average project of mine, there would be like 10 to 15 of those tops. So they're just like sitting nicely in their own file. And then throughout the code, I can just use them like that, user ID of 1 to 3. But keep in mind that we rarely have to use hard-coded ones, so we're just passing them around. And we're also parsing them from JSON, right? And we don't want to be manually converting models, of course. So I have found that it's really easy to set up the decodable conformance, where we decode our type from the single value of a string. And so the model that we previously had like this, with IDs being a string, we can just go and replace them to our new strict types. So just with this small extension, we can switch from strings to concrete ID types. And this helps with discoverability as well. So this is a screenshot of search from one of my projects where I'm just searching by my user ID. And you can see I'm not even using matching case. And it finds all of the places where my user ID is used. It's stored in the accounts, and it has, it's stored in the API client, and it's used in one of the cached models, and passed around in some direct messages. This was an app I built for trying not to use Twitter as much, and then I had to kill that because the API now costs like $40,000 a month. So RIP my app. Yeah, but you can see here, I'm using my user ID as a type. I actually have another type called other user ID. Because if you think of it, they're not really compatible. Those API endpoints that take my user ID can give me much more information about my user, or tweets of my user, compared to endpoints that I will call with another person's user ID. So I have created these types, and they are separate, they're not compatible. And as you can see here in the search, it's completely different files. Okay, they're also in cached models, but also in the direct messages, but it's completely different situations. For example, when I want to open a URL, like a deep link with another user, it's another user ID. I don't want to open a deep link with my own user ID. So that helps me separate those things. And there's actually not, I don't believe there was a single place where those two have to be converted to each other, because it's different use cases. Yeah, so just to quickly summarize there, strongly typed identifiers help us with compile time guarantees, and they make code more intuitive and self-documenting. They also help us avoid these typo-based errors when we pass the wrong string to the wrong place, and they also offer better code completion, which we desperately need, I think, a lot of the times. All right, now let's have a look at safer assets. So assets like images, fonts, files are notoriously very like UI level things. How do we spot that an icon is missing? We can see it in the app. But what if it's in some remote corner of, of settings or some rare user flow that you don't smoke test every time? Then we don't know that the assets are missing. And true, there is snapshot testing, but not a lot of small-sized teams use that. So what I like to do is define constants for the assets, for like fonts, images, everything, basically. And this can be in a small app, just an enum with the cases. It could be something like a protocol and structs conforming to it, depending on how complex your use case is. And another benefit to that is that if we conform this little enum to case iterable, then we can iterate in the unit tests over all cases, which is provided by the compiler. So we are not forgetting to test any of the cases. And we just verify that the image is missing, or localization is missing, or the font is missing, or hopefully not missing. And there are third-party tools that do this. And in big projects, it's a good idea to automate that, of course. So there's SwiftGen, there's RSwift, and this is an example from RSwift. And in Xcode 15, we're getting that out of the box, where it will generate constants for colors and images, and hopefully like for fonts and other things in the future. And this will apply to all projects. So if you just start using your project with Xcode 15, then you should get these things set to yes, and you could start using these constants. All right, and then the last section is refactoring with a compiler. So what does that mean? Like when we are refactoring things, like sometimes we get all these red errors, and we get frustrated that, or I get frustrated sometimes, like nothing's working, type of, you have to roll back and start your refactoring again. But in some cases, I actually like using the compiler and using those errors to my advantage. So let me show you a small example of how I do that. So let's say I'm working on a legacy code base, and which I sadly do a lot of. And then there's this possibly a singleton, like huge class, and I see this variable that is static. You can set it from anywhere. It's set to -1. It's terrible. And then there could be, various uses through, various uses of that throughout the code. What's happening? Yeah, and even bugs like, trying to load a user of -1 before we're logged in. So what I will do is I would go and just change that variable to be an optional. And I would not even necessarily search through the project where it's used. It's just whenever I encounter a variable that shouldn't just be var that's open that much, I just like change it to optional and see what happens. And then the compiler will bring out all the errors, like the errors in the places where we're not unwrapping the value. So then I could go and just do a small refactoring and unwrap the value explicitly and fix a bug on the way. And that can be a small commit, a small pull request, a very safe change, because we have basically just changed how we, on the code level and not on the logic, really. So then the next thing I would do is set that to private set. And again, just build. It takes 1 second to type private set, and then just hit build. And then the compiler will show us all the places that are assigning this property. And otherwise, it could be really hard to search for that, because here it's just user ID equals something. There could be many pieces of code in the source files that match this string. So just using the compiler for that I find it really handy. And then, can again refactor that by creating a small function for resetting the user ID and using that instead of directly setting the thing. so we can keep the variable private set. And so this again can become a really nice small commit that is not really changing anything in the behavior, but just refactoring the code. Yeah, and this is how I like to use the compiler for helping me navigate legacy code bases. And yeah, to wrap up, like I love compiler checks, compile time checks in Swift. They help with so many things like refactoring huge code bases and operating with IDs safely, like checking that we're not missing assets, help to write more declarative UI updates if we're not using Swift UI. Defer can help prevent memory leaks and yeah, avoid hanging spinners. I hope you got inspired and can take this mindset with you, and that can help makes your apps better. So yeah. Thank you. Yeah.